Hey everybody, this is a quick video. Kika had a question on the fourth number 10 regarding the natural log of x to the fourth plus 1, particularly b and d. Um, and I honestly don't know what happened. When I scanned this, it kind of scanned backwards. I didn't think I scanned it backwards. So, well, let's go over the concept behind this. Um, so, Again, an inflection point only occurs where the second derivative is equal to 0. Okay, and we've seen that before. Okay. If the second derivative of a function is 0 at a certain point, it doesn't guarantee that an inflection point exists. Okay, and then we go back up to here, since this would be, whoops, this would be the next page of this, even though it's above. So, for example, if they have x to the fourth, first derivative is 4x cubed, second derivative 12x squared. No pasa nada. All right. When x is 0, the second derivative is 0. So we think that there should be an inflection point at x equals 0. But we just saw, right to here, just because a second derivative is 0 at a certain point, it doesn't guarantee a point of inflection. So what we have to do is look at to see if there's any change in sign. Okay, so again, second derivative is 12x squared. When x is negative 1, the second derivative is negative 1 quantity squared, 1 times 12, 12. That's a positive number. Okay, and again, negative 1 is on the left side of 0. Okay, go on the right side of 0 when x is 1. The second derivative, as you can see, is also 12. Therefore, because there's no sign change, right? The second derivative does not change sign before and after 0. There's no inflection point at x equals 0. Okay, so keep that in mind as we go over this number 10. Okay, so we've got the natural log of x to the fourth plus 1. Again, 2 marks, plug in 0. The natural log of 1 is 0, right? E to the 0 is 1. The natural log, or the log of any number, is the exponent of the base, no problem. Find the set of values of x for which f is increasing. In other words, when does the graph have a positive slope? Okay, so you find the derivative of f of x using the chain rule, right? The derivative of the natural log is 1 over x, but I use the inside function, so 1 over x to the fourth plus 1 times the derivative of the inside function, 4x cubed. This is where you just have, I guess you have to be a little thoughtful about this. X to the fourth will always, 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 always give you a positive number. Therefore, 1 over x to the fourth plus 1 will always, always, always give you a positive number. All right, does x cubed ever give you a negative number? Yeah, when x is negative. So when x is negative here, a negative number to the fourth power is positive. When x is negative here, a negative number to the third power is negative. So when x is negative, this will be a decreasing function. We'll have a negative slope. When x is positive, we'll have an increasing slope. And when x is 0, obviously, right? When x is 0, we have a minimum or a maximum. Right? What I have for you is the graph of that. So this is the natural log of x to the fourth plus 1, and we can see physically what happens, right? All right, this dotted orange line is the tangent at any value of x. So when x is 0, in this case we have a minimum. Past 0, positive, 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 positive. Okay, and this is what, it's kind of crazy, but this is what the first derivative looks like. So x equals 0, right? My first derivative is 0, all right? And remember, the green function is the derivative, and the derivative gives you slope. So when I go here, when x is 1, you can see that my slope is 2.07. Yep, on the green, which is the slope, it's about 2.07. Okay, if I keep going, say when x is 4, remember the green graph is my derivative function. Looks like my slope, wow, is 1. That's interesting. Okay, all right, and there's the 1 there. Okay, so no problem. So when I look at this, so slope is increasing, and then there's probably a point of inflection, and I still have a positive slope, but that positive slope is obviously decreasing. Okay, so remember, on the first derivative, mins and maxes indicate points of inflection. So it looks like right around here, I'm going from concave up to concave down. So I'm still positive slope, but this is where I'm going to have my maximum slope. Right? Still have a positive slope, but that slope is decreasing. Similarly, on the left-hand side, right? Negative slope, 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 negative slope. Sorry, that's why I have this little orange guy here. All right, so it looks like when x is negative 4, I have a slope of negative 1. Right? When x is 2, right? Excuse me, when x is negative 2, it looks like my slope is negative 1.88. Negative 1.88. Okay? And it's, again, I want you to focus on this slope, and this slope is of the tangent, which corresponds to the green function, the first derivative. So it's increasing well, excuse me, the slope, right? So, right, I want you to think about when this starts to change. So negative 2.17, negative 2.22, negative 2.23, 2.24, 2.5, 2.6, 2.7, 2.8. Now it goes back to 2.7. So there must be a point of inflection somewhere here, which kind of makes sense. That's the minimum of my first derivative. So there's a point of inflection here. It's where it goes from concave up to concave down. So this still all represents a negative slope. As you can see here, all of these slopes are negative. But the greatest negative slope is here. Right? Okay, I know when we've looked at when we've looked at the derivatives and the function on the same graph, it is a little tricky. Okay, let's look at letter C. All right, they're giving us the second derivative, and they say the second derivative equals 0 only has 3 solutions, 0 and plus or minus 1.316, which, if we look at that, looking at the, okay, here's our second derivative, right? I'm going to put that on there, okay? That's where our point of inflection, well, that's where we think a point of inflection is, right? Negative 1.316, that's the minimum of my first derivative. Okay, that's a 0. That's where my second derivative is equal to 0. And this is where my second derivative is equal to 0. Positive 1.316, which is the maximum of my first derivative. So we know there could be an inflection point. Okay. Find the value of the second derivative when x is 1. You know, just plug in 1 and see what you get. So it's 2. Okay, no problem. Then, hence, show there's no point of inflection on the graph at x equals 0. Remember at the very beginning of this video I said, if to the left of 0, the second derivative is positive, and to the right of 0, the value of the second derivative is positive, then there's no change in sign, and therefore no point of inflection. Similarly, If to the left of a particular x value, the second derivative was negative, and to the right of that value it also is negative, there's no sign change, no point of inflection. So what I just did, I said, oh, okay, f of -1 is also positive. How do I know that? All right, put -1 to the fourth. -1 to the fourth is +1. 3 minus 1 is 2. That's going to be a positive number. I'm squaring that. That's going to be a positive number. So all of this is positive. Again, therefore, since there's no sign change at x equals 0, right, at x equals 0, there's no point of inflection. Okay. There is a point of inflection on the graph at x equals 1.316. So it says, okay, sketch the graph of f for x greater than 0. So here's my 1. Here's my 2, here's my approximate 1.316. I'm going from concave up to concave down. Again, I would assume this is a paper 1, because you're not really doing anything that crazy. All you're just basically trying to show is that, again, you know that f of 0 is 0. So on my main graph, f of 0 is 0, this point right here. Okay, and again at 1.316 I have a point of inflection, so it's going to go concave up to concave down. All right, I hope that helps. And again, I would just go back to here. And again, no inflection point because the second derivative does not change sign. Okay, if there is a change of sign, then yes, there's a point of inflection. Okay? Right? If there is a change in sign, then there's a point of inflection. No change in sign, then no inflection point. Okay? Again, one more time to look at that graph. Again, it looks really crazy. The red is our main function. Okay? No problem. The green is our first derivative. The first derivative is the slope, gives us the slope function of the main function. So negative slope, 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 0 slope. These are all negative slopes. The biggest negative slope, that's where my point of inflection occurs. Still negative slope, negative slope, negative slope. Okay? Then, again, focus on the red graph, positive slope, 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 positive, blah, 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 blah. Okay, again, the first derivative, slopes of the red graph. Positive, 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 positive. There's a max at my first derivative. It must be the max slope of the main function. That max slope could be a point of inflection, and it is 1.316. And that's where, again, the max, so if I, now second derivative is the slope of the green. If I'm here, right, if I'm here at the max, my slope would be 0. My slope would be 0. Where is that happening? 1.316, a point of inflection, right? Positive slope to negative slope. Positive slope to 0 slope to negative slope. So I'm changing sign at 1.316. Positive slopes, negative slopes. Remember, blue is second derivative. Similarly, slope at this minimum is 0 at negative 1.316. Okay, there's a change in sign of the slope. Again, negative slope, negative slope, negative slope, negative slope, slope of 0, positive slope, positive slope, positive slope. So second derivative, negative slope, negative slope, negative slope, negative slope, negative slope, slope of 0, positive slope. But at 0, positive slope, positive slope, positive slope, positive slope. No sign in, no change in sign. Woo! All right, I hope that helps. I'll be around this weekend, and let me know if you have any other questions. Okay, have a great day.